A computer architect walks up to an elevator and sees the sign, out of order. What's he going to do? What's he going to say? Even better, he says, and gets into it. Welcome. My name is Christoph Tüscher. I'm a professor in electrical and computer engineering at Portland State University. And in this short presentation and in my paper, I will muse about a golden age for computing frontiers, but is it a dark age for computing education? And you can guess the answer already. My perspective is mainly from the US educational system, so your country or your university may not be in the very same position. Your curriculum may be different. You may be addressing some of these things that perhaps we don't, but clearly, as you will see in the US educational system, the way we educate our computer engineers, our computer scientists with respect to novel emerging technologies seems to be lagging quite behind. And I guess I'm spilling some of the beans already here. So let's start at the beginning. If you're like me and you took a computer engineering, computer science, or computer architecture class some 20 years ago, you probably used Hennessy and Patterson's famous computer architecture book, which is still considered sort of the Bible of computer architecture. And I'm sure you learned about out-of-order execution in a simple pipeline. The edition I have here is the second edition, almost has collector's value, I guess. The first edition came out in 1990 and it had 784 pages. If you're a student today, you're probably using the 6th or the 5th edition. I've got the 5th edition here, which has a little less than 936 pages, which is the number of pages the 6th edition has. The question you may want to ask is, are these 152 additional pages in the 6th edition with respect to the 1st edition, are these covering what happened in the field over these 27 years? And I think that's a fair question, and I guess you can already anticipate my answer. My answer is probably not, right? It covers the foundation, but many of the emerging trends in computer architecture that we've seen in the last 5 to 10 years are simply not covered by this foundational book, by this comprehensive book on computer architecture. I looked specifically at the 2nd and the 5th edition that I have here on my desk, right? Out-of-order execution topics had 4 lines in the index for the 2nd edition, whereas in the 5th edition there were about 20 lines. So clearly topics were added, and that's a good thing. But is that enough? Was that enough? And are students today getting really the background and the things they need to know to be successful in this new and emerging field of how we build and design computers today and not 30 years ago? I think it's quite obvious that a decade ago we didn't talk about deep learning, memoristic devices, in memory computing, and neural engines, and you name it, right? Basically all the topics of this exciting conference are things that emerged over the last 5 to 10 years to some extent and took off also quite radically in the last 5 to 10 years. A good example, I think, is Apple's M1 processor, which has this new neural engine that accelerates machine learning algorithms. Right, we can ask ourselves, do our students have the background to design such a special part of that chip? Right, where would they get that knowledge from? Not from Hennessy and Patterson's book. That much is clear. Right, it covers some of the GPU things in the more recent editions, but even that is questionable whether that's enough to really, bootstrap your computer engineering career. So it seems there's a problem, and that's precisely what I want to talk about in this short presentation and in my paper. So ACM since 2000 and I don't know what, 2004 I think, no actually since 1960s is providing sort of guidelines for computer education curriculum, and what I'm showing here is one for undergrad students, computer education knowledge areas that every undergrad student should go through in an computer engineering curriculum. And you can see the latest update was 2016. That in itself is perhaps a bit of a red flag, right? This is supposed to be, I guess, recent, but it doesn't seem to be quite recent. And I'm comparing to 2004. And what you can see, there is a number of differences here between 2004 and 2016, the recommendations for a undergrad curriculum, computer engineering curriculum. Clearly many topics disappeared, some new ones appeared, and such as software design instead of software engineering, right? Seems pretty similar. There's still digital design, digital logic, embedded systems, some computer architecture and organization. But really, I guess what you can see directly here is that none of the emerging topics that we talk about at this conference really is covered by that computer education suggested curriculum. And that seems to be a problem, right? Also, the topics were reduced from 18 to 12. They do note that this is not a complete list, and that a solid curriculum needs to be supported by additional topics, which seems quite obvious, but they're not listed specifically. Good. What about graduate education? And I looked at several universities. I'm showing here one, Boston University. Here's the list of graduate electives that they offer. You can see quite a solid emphasis on obviously computer architecture, high performance programming, multi-core systems, right? This is sort of like, okay, going in the right direction at least, but still there's a lot of sort of traditional still digital design and computer hardware testing, fault tolerant computing topics, including VLSI designs. Surprisingly, there is still some analog RF design that's, I guess, questionable for computer architecture, but maybe it's coming back because of all the analog design things that are getting back into computer architecture with neuromorphic engineering, membristors, and all these nonlinear analog devices that have been appearing over the last decade or so. So perhaps not a bad thing, but still you can't really see any of the more exotic emerging topics on that list either for graduate education. Good. So next I was doing some searching in a database by Elsevier, the engineering village Thesaurus, and I looked first at computer architecture. How the number of records over the years evolved for that specific term, computer architecture, in that database. And you can see the years on the x-axis, the y-axis shows the number of records in that database. And as it's quite obvious, there was a peak sometime in the late 80s, and then things started to flatten out and decrease quite a bit, and the trend has been quite decreasing since then. So there seems to be clearly, not just by looking at this data, there seems to be an increasing gap between sort of the old way of designing computers and the new way of designing computers, right? This clearly suggests that it was an old way that peaked somewhere in the 1980s, the traditional sort of computer architecture field, which has been decreasing since then. And as we will see on the next slide, many of the topics that we talk about at this conference are exploding in various ways, such as the terms neural networks, memristors, neural chips, quantum computing, embedded systems. Notice this is a log linear plot, so and I, for comparison, included computer architecture. You can see, again, computer architecture peaked and then decreased. And so all the other terms listed here with the different colors are essentially exponentially growing. And you can, for example, see that neural nets is more than a tenfold increase in the amount of terms appearing in papers in the records of that InSpec database compared to computer architecture. And right? That again suggests that a disconnect between what's happening in the field and what we teach at our universities. Good. So let me recap here. I think it's quite obvious that the computing foundations are not going to be obsolete in the next decades, right? We're not going to get rid of traditional processors and GPUs and whatnot. This stuff is here to stay. So those foundational books, we can't just get rid of them, because that is knowledge that our students still need to be very familiar with. However, I think the technological process has accelerated, probably as in no other field. Things have quite dramatically changed for computer engineers, and a lot of emerging sub-areas such as neuromorphic engineering, quantum computing, in-cloud computing, and memory computing, and computing with novel devices such as memristors and memcapacitors, and resistive RAM, and you name it, right? These are quite complex sub areas that interact with a lot of other disciplines, including biology and physics and material science. So specialization has become a lot harder, right? It's very, very difficult for a single person to understand several of these sub areas. I think it's also quite obvious, and the data shows that the computing education has not kept up with that blistering pace of recent emerging computing trends and paradigms and the hardware, right? I think our students are sort of like screaming and knocking down our doors to ask for more neural network classes, for more data science and things like that, because the job market really expects graduates to be familiar with many of these areas that we do not seem to sufficiently cover, right? I can tell you an anecdote from our department. Several years ago, a faculty retired, and a faculty who was teaching our neural networks course, we decided to kill that course because there was very, very little interest in neural networks at that time. In these days, as you can imagine, students are knocking on our doors, and they want more and more neural networks courses, and we're in the process of satisfying that demand and increasing the courses we offer in that area. But that was obviously due to the job market, because students are asked during job interviews, do you have those skills? It would be really good if you had those skills, and can you program in Python, can you do TensorFlow and all these things, and can you implement a neural network and whatnot, right? Those skills really are very much on demand on the job market. So what do we do about that? Well, is there a way we can avert the crisis? I think I alluded to that a little bit earlier. Because of the complexity of these subfields and the specialization required and the cross-disciplinary aspects, it's probably impossible to sort of shoot for creating the computing polymath a student who knows a bit of everything, right? The fields are too fragmented. It's too complicated to really get into the weeds of all of these materials. So that's probably not the way to go. And we can look at physics, right? There isn't really physics students in physics who know everything about theoretical physics and experimental physics and all the other subfields, right? You specialize in a field and you pretty much stay in that field. And so that brings me to the second point. I think what we can draw inspiration from is precisely from the field of physics, where more specialization was the way the field went, and that at least helped to some extent to alleviate that crisis in their field. But I think in computer engineering it's actually much more dramatic, because the field has moved much quicker. And so specialization and fragmenting the field of computer engineering into various subfields may really be the only possible solution here. And we can see trends with that. We can see much more specialized graduate programs, right? Maybe we need to think about graduate programs for neuromorphic engineers, for quantum engineers, you name it, right? These are all subfields that are complex enough and rich enough to really merit majors in that area. It seems that over the last 5 to 10 years, the master's degree has become the new bachelor's, partly because industry realizes that the bachelor just doesn't offer enough depth for students to be successful in these fields, right? You really need to have a lot deeper but also broader understanding of these fields to be successful, let's say as a computer architecture major, right? There's so many things you have to know that you just can't squeeze into a bachelor's degree, so a master's degree seems to be the new trend. We can also see the appearance of what many call the micromaster's degrees, where you really become or take degrees that are highly specialized, let's say data science or VLSI design or whatever it is, right? Very narrow field where you get expertise and can get credits and credentials. And then you can sort of use those micromaster's degree to build a skill set that industry wants to see in today's students. There's problems with that, with accreditation, and how do these things fit together, and so it's lots of unanswered questions. But it seems that's a market that has evolved mainly through MOOCs and other online programs, and students seem to enjoy those and seek those degrees specifically. And I can speak for some of my students who wanted to get into neuromorphic engineering and learn more about neural networks. Well, they do take these online classes and they rather quickly get up on speed, and so it seems to work for many of the students. Why did the computer engineer retire young? Well, he had a lot of cash. Thank you for listening. I hope you enjoyed it.